Okay, in this video, we're going to use Simulink and this type of analysis to kind of figure out, what are acceptable, okay, I'll call them motion plans. Maybe we'll call them trajectories or missions, but it's really how do we move it and operate the forks at the same time, all right? In that example that we constructed very quickly, we can kind of see a important violation, which is that the rear axle is going to carry a negative load, which we know will mean it will tip over, all right? So that cannot occur. Well, it's mostly just kind of working with these two blocks, and really the easiest way, I think this works, let's fix it, is don't let it go backwards. Not sure that would be a real requirement we would impose, but let's at least show how this would work. So it's going forward and lifting the forks and everything. And let's look at the data inspector, and absolutely that fixes the problem. All right, and again, it's I'll call it a biased design, and again, it's nothing wrong with that, but they're kind of designed to move forward. All right, and the fact that the loads in front of them works a little bit better dynamically. Right, but anyways, I think in truth, in reality, sometimes we do want to go backwards. So let's figure out how we do that. And so just to remind you where we were with that, let's make it -5. Got it going backwards. So again, we got that violation. Well, you know what? I think it might be readily apparent that kind of I'll call the dynamics that are leading to what we're observing on what's carried by the front and rear axles. Well, part of it's the acceleration of the vehicle, but the other part is that the forks are going up. And I do believe they superimpose, and perhaps that's, maybe a bad thing to do. Although, again, we saw if we move it forward, things work real well. And I want to get it right up here, and I think it's readily apparent that we try to accelerate the vehicle, backwards when the forks are up. We got a much larger moment arm associated with this load right here. And I would suggest let's travel, accelerate backwards and then raise the forks. So that's the way we're going to do it, right? And so again, here's the rack lift. This is starting at 2 seconds. And again, our acceleration takes place for 2 seconds on horizontal movement. So I think it's safe to say if we make the rack lift start at 5 seconds, we'll be able to separate those pretty well. So let's look at that. There again, they go up. Okay. All right, and there you can kind of see, oh, okay, that first little parabola, of course, that's associated with the acceleration. And the little wiggle right there, that's really associated with the lift of the forks. But really that acceleration is really too much even if the forks are in that lower position. So that means we really need to reduce that acceleration. And so I think the last change I'll make, and I tried this with 4 seconds and it barely violates, maybe I'll do it 5 seconds this time. All right. Again, that's the smooth velocity. So let's do one more run. All right, and look at that. We still got a little bit. So there's a little bit of work to do, but hopefully I'm kind of showing you Simulink is the type of analysis tool that can kind of handle this. And again, really these mission plans, they will take place through the software that operates the system, and certainly there will be a very important state machine put in place that will really kind of monitor conditions like this and really protect the equipment and make sure that, hey, this is going to lead to a tip over, I'm not going to allow you to do it. I'd say the next step probably is to reduce kind of the rate at which we're going to raise the forks. Well, I think moving forward we'll do at least one more kind of using Simulink to make good decisions type of demo. And with that one, I'm going to introduce, again, the idea of running lots and lots of runs and then automatically generating a report so that we essentially create like a test matrix that will absolutely link to like requirements documents, that sort of thing, and really make sure that as you design these systems, which includes not only designing, well, from the MathWorks perspective, we always talk about designing missions and controls, but really designing equipment, from, I'll call it the mechanical side of this, are your design choices okay? And how's that going to affect your ability to meet requirements? So I think that'll be a pretty interesting one too. So thank you for watching.